Hi everyone and welcome back to Digital Design with Verilog course. So today we will start a new lecture, that is we'll discuss about continuous assignments, operators and operands, and of course I will give you few homework assignment questions. Okay, so we will learn a lot of new things, so like try to have patience and watch the video everything in full focus. Okay, so because today will be a bit on the like the level will be a bit on the higher side. Okay, so like although everything will be easy only, but still few things may be new to you guys. Okay, so let's start with continuous assignments. Although we have already learned about what is continuous assignments, still let's understand what is continuous assignments. Continuous assignments are fundamental in data flow modeling, allowing values to be driven onto a net. Basically I'm continuously writing something, right? Reg is just for storage. Okay, but continuous assignment means like this wire I'm connecting it to VDD supply. That means constant, it is like 5 volts, continuously it is driving 5 volts. Okay, that is what we mean by continuous assignment. These assignments provide a higher level of abstraction compared to gate level modeling, effectively replacing gates in circuit description. They are initiated by the assign keyword. Okay, so we have already learned what is assign keyword. Today also we will learn a bit more about assign keywords. Okay, so like this is just a format syntax of assign keyword. So like this, right, don't get worried up from this. This is just for describing how we write the assign, right? How we write this continuous assign. We write it like this assign, then we write the drive strength, then we write the delay, and then the assignments. Okay, whatever we want to do, I will show you an example, there we will understand this. Okay, let's move on to the next slide. So if I move on to the next slide, if I see that on the left hand side of a assign statement must be a net, that is basically a wire. Okay, so this I have already told you before as well. Again I'm reiterating it, that on the left hand side of a assign statement there must be a wire. Okay, on the right hand side it can be a reg or anything, doesn't matter. Registers are not allowed. Okay, it can be a concatenation of vector and scalar. So what is a concatenation operator? Today only we will learn about it. This here it is written concatenation. Basically what it is doing, that this sum has 4 bits, cout has 1 bit, so total, right, the output, this is 5 bits. Okay, and this also I'm adding two 4-bit numbers and a cin. If I add a two 4-bit numbers, what will be the maximum value that I will get? The maximum value that I can get is a 5-bit number. How is that possible? If all of them are 1. Okay, if all of them are 1, then what will be the output? Output will be, this will be 0, this will be okay, this will be 0, this will be 1, this will be 1, this will be 1, and this will also be 1. Okay, so ultimately I'm getting a 5-bit number, right? So if I have a carry in as well as 1, then this also will be become, this also will be 1. Okay, if my carry in is 1, okay, this also will become 1 then. Okay, this also will become 1. So like it totally depends, so I am getting a maximum 5-bit value. So if I just store it in sum, it will not be able to store the whole 5 bits, right? It will still concatenate the MSB. How do I store it? I store it in cout. So sum is 4 bits, so the final MSB after this comma will be stored here. The last MSB, right? MSB will be stored in cout, and the other 4 bits will be stored in sum. That is what we do in concatenation. Don't worry, I will explain this in detail in later on. Okay, later on today's lecture only. Okay, so this one is simple basic assignment. This is the vector assignment. So it is a wire of 16. So we have 16 wires here, right? 16 wires we have. Okay, so and what I'm doing, I'm just doing the XOR of address 1 and address 2 bits, 16 bits. Okay, so this is bitwise XOR. I will explain this later on, don't worry about it. So I hope you understood. The continuous assignments are always active, meaning any change in the right hand side operands triggers a re-evaluation of the expression and updates the LHS, right? So basically it is a wire, right? And if this wire is connected to any other wire, so if there is some change in this wire, if it goes from 0 to 1, the same will be reflected in the second wire as well, right? It will go from 0 to 1. So that is what that is the definition of continuous assignment. It should update continuously. It is a continuous signal. Okay, the RHAs can include registers, nets, or function calls. These can be scalar or vector. Okay, so the RHAs can include registers, nets, or function calls. These can be scalar or vector. Delay values allow control over the timing behavior. Useful modeling techniques, real world circuits. Okay, so yeah, delay I will show you how do you do delay. Right hand side can be anything. Okay, So like, okay, now we are coming to the concatenation operator only. So let's discuss about this concatenation operator in detail. So I hope you know delay I already have explained a bit on gates as well, so I don't think it will be that difficult. If I just write here #5, that means you understand that after a delay of 5 this will get executed. That is not that difficult to understand. Now let's understand concatenation operator. So the concatenation operator is shown like this, curly brackets. The curly braces in Verilog are used to concatenate multiple signals, scalars or vectors into a single grouped expression. In this case, Cout sum, right, is concatenated result of Cout, which is a single bit signal, and sum. So basically, let's say the result, what do I get? Like here only I have written, let's say the right hand side result is 1001. So obviously sum can only store the 4 bits, so this will be sum and the MSB will be stored by Cout. Okay, that is what we do here, right? So sum has 0001 and Cout has 1, the MSB, right? If I write concatenation like this, so the MSB will be stored here and all the other bits will be stored here. That is how we represent concatenation. Now I think pretty straightforward, pretty simple to understand this expression. Okay, now let's understand about implicit continuous assignment. So Verilog allows placing continuous assignment directly during net declaration. Only one implicit declaration assignment is permitted per net. What does it mean? Basically, if I want to assign a value here, right, out in one, I can directly do it. So while initializing, if I want to assign a value, I don't need to write assign. Verilog understands internally. Assign is understood by Verilog internally. So Verilog understands this, that here, right, I have a assign statement. Okay, it understands that okay, this is a continuous assignment, so it is implicit to the command. But let's say if I say here that my my I will write another statement. This out is here, then I write another statement, out is equals to 1. This, right, Verilog will throw a error. Why it will throw error? Only once I can do this, while initializing. While I am writing wire out, so I have a variable named wire out. Okay, while initializing, this is valid, I can do it without assign statement. But directly in the next line, if I write out equals to 1, Verilog will throw error. How do I fix it? I have to write assign. I have to write assign here. If I write assign here, then Verilog will not throw any error. So that's why it is telling once it is allowed, after this we are not allowed. After this we will not be able to do something like this. Next is implicit net declaration. When a signal name appears on the LHS of a continuous assignment without prior declaration, an implicit net declaration is inferred. Okay, so when a signal name appears on the left hand side, so when a signal appears on the left hand side of a continuous assignment without prior declaration, an implicit net assignment is there. Okay, so basically what happens, let's say I have not defined what is out. I have not defined what is out. Note that out was not declared in the scope here. Okay, but still Verilog understands, okay, I'm trying to do some continuous assignment of I1 and I2 to some value variable out, but this out, right, is not defined like this wire out. I have not defined, but Verilog internally will make a variable of type wire out. It will make it. It will not throw out any error. It will make it. Okay, and it will create it. Then I can use that out anywhere else. So that is implicit net declaration. Automatically Verilog, like here in this command itself, implicitly the net is getting declared. Here I declared the Verilog, but the assign statement is implicit. Here the net is not declared, but the assign statement I have written, so net is automatically implicit in this command. Okay, so that is the case. Next is delays in continuous assignment. So how do I do delays? Like this, if I write assign 10 delay, that means a delay of 10 time units is applied. Okay, so basically if in1 in2 is this, so I am doing the and operation of in1 in2. So I have started from here, right? So if I have started from here, but it will start from 10 below, because before this in 1 into I don't know what are the values, so there will be XX sign. Then at 10 nanoseconds or 10 time units, my assign statement understands that now if it finally receives this data at time unit 0 at the 10 nanoseconds. So now as I am doing AND, 0 and 0 will be 0. If I reach here at 20 time units, my in1 and in2 are 1. So I should get 1 here out, but it is not 1. Why? Because I have a delay of 10. So it performs the operation in 1 and in 2, right? It performs it, but it stores or assigns at a delay of 10. So you see at 20 time units, after delay of 10, that is 30 time units, the output is going to 1. So that means there is a delay of 10. So that is what is written over here only. Same thing is written over here. Okay. So I hope you understand the like a delay concept. So this is implicit continuous assignment. Okay, it is same as this, that I am defining wire out, then I am doing assign delay of in1 in2. It is same, single line and 2 lines. So like why am I teaching you? Just because like knowing these things is easier, because it makes your code very simpler and like less clunky. Okay, so this is implicit assignment. This is same as this, right? I'm doing the same thing here. Both will not throw any error, both will work totally perfectly. So there is another thing known as net declaration delay. So if I am declaring this net at a delay of 10 and then I am doing this, so this right out value for the 10 seconds, 10 time units, it will be x. Okay, it is same as this one. Both of these statements are similar. Here I am assigning after a delay of 10, or I am declaring after a delay of 10. Both statements are same. Okay, so now we will understand about expressions, operators and operands. So there are many types of operators and operands. So basically, what is expression? So whatever we learn, we will use this in Dataflow. Of course, we will use in behavioral as well. So Dataflow modeling describes designs using expressions instead of primitive gates. In gate level modeling, we used AND gate, OR gate, but in Dataflow level modeling, we'll use these expressions. What are these expressions? We'll understand them slowly one by one. Okay, so expressions are combinations of operators and operands used to produce results. These constructs represents operations and computations. What are operands? Operands represent data being operated upon and can include constants. Because here, right, in this C equals to A minus B, C equals to A minus B, A and B are the operands, and this subtraction sign is the operator. Okay, this subtraction sign is the operator, and A and B is the operand, and C is the result. Okay, and this A minus B is the expression. Okay, so I hope you have understood what is operand, operator and expression. Okay, so there are many types of operator. These are just example I am showing you. So we will not use logic gates. We'll directly use like AND operand, not operand, like that. I will show you with example. So there are many types of operands in operators in Verilog. These are mainly the types of operators. Okay, there can be few more as well. I may have missed few, but mostly these are the operators. So we have arithmetic operators like multiplication, subtraction, not subtraction, sorry, division, addition, subtraction. This is the modulus operator. Modulus is just gives the remainder. Modulus gives us a remainder. Let's say 3 mod 2. What is the remainder? 1, right? 3 mod 2 remainder is 1. 4 mod 2 remainder is 0, because it is totally divisible. Okay. Then power, exponent. Okay, we can do 2 raised to power 2, right? 4. So we can use this power operator. Then we have logical operator. Okay, logical is, this is not, logical negation, logical and, logical or. Then we have relational operator, which is greater than, less than, greater than equals to, less than equals to. Then we have equality operator, equal equals to, not equals to, triple equals to, that is case equality. We'll understand this later on. Not case inequality. Okay. Then we have bitwise. Here also we have bitwise negation, bitwise and, bitwise or. So you might have a doubt, what is the difference between this logical and negation and this bitwise negation? So logical negation actually performs like we will understand this, but bitwise negation is, it performs on a single operand. Okay, it performs on a single operand. Logical and also performs on a single operand, but it performs bit by bit operation. It performs bit by bit operation. That is why the name is bitwise operator. Logical operators, they do not perform bit by bit operations. They perform a bit like differently. I will explain that when the like that topic will come. Okay. Then we have reduction operator. Here also there is a and sign. Okay, not and, all this. So don't worry, we'll understand this slowly. Shift operator is like bitwise shift. If I right shift or left shift, bits. Okay, so this is what S shift operator is used for. Then concatenation operator already have been explained, and replication operator. Replication operator simply replicates whatever I have. Okay. Then conditional operator. This is a ternary operator. This is used in muxes. So this also I will explain. Okay. So let's understand the bitwise operators. So let me start with bitwise AND. So bitwise AND, basically, let's say if I have a 2 input NAND gate, right? Not a NAND gate, sorry, AND gate. If I have a 2 input AND gate, okay. So let's say I want to do bitwise AND. So what does bitwise AND do is, like, let's say I have two numbers 1100 and 0110. Then bitwise AND will do bitwise AND. Okay. So basically the LSB will be ANDed. So this will be 0. This next to LSB 0 and 1 will be 0. This again individually the bits will be ANDed. This will be 1 and this will be 1 and 0, that is 0. Okay. So what is the use case of this bitwise AND? First use case is of masking. What do I mean by masking? Let's say I want particular bits from a number. Let's say my A is equals to 1100 and I want these two bits. Okay. So how will I like get the two bits? I only want these two bits from this A value. So what I will do, if I do AND with a mask, what will be my mask? As I want these two bits, I will make these bits in my mask variable as 1, other bits I will make it 0. Okay. So only the information in these two bits will be stored in the result. So if I do right now, result will be A AND mask. Okay. So basically what we will get is this will be 0 1 0 0. So the two, if you see, the two bits has been totally copied over here, right? So that is what it is used for, like masking and all those things. You will understand masking when you will go into the industry and all those things. Okay. So that is what this like bit is like AND, bitwise AND is used. Another use case we have for this bitwise AND is for force reset. Okay. So this masking is basically retain specific bits, and next one is force reset. So let's say I want to forcefully make few bits 0. So I will reset that bit. So let's say I have this number, okay, and I want to reset the MSB. So what I will do, I will do the AND operation. So this 1100 I have, so I want to reset only the MSB. I want to keep other bits same. So I will make this 0 and other bits will be simply 1 1 1. Okay. So what it will do is it will just simply do the reset. This will be 100. That's it. Okay. So this bit has been reset now. So that is what a bitwise AND is used for. So similar kind of thing we can do with bitwise OR as well. Okay. So similar kind of thing we can do with bitwise OR. So the same thing I want to discuss about bitwise OR. Just it will be bit opposite. Okay. So if I have a bitwise OR, 2 input OR gate. Okay. Now if I have a 2 input OR gate, right? So if I want to do masking, I can do masking. Again, I have the same number, right? This what was the number? 1100. Okay. But I want to store the middle two numbers. What will I do? I will make all the other digits 1, and whatever I want to retain, I will make those digits 0. Okay. So basically what will be the OR of this? The OR of this will be simply 1 1 0 1. Okay. So basically I will ignore the, I will just focus on the two bits which I wanted to retain. So I have retained, right? These two bits have been totally copied over here. So basically this is the first use case, masking. Okay. Then the second use case is force set. Force set. We can set the values over here. We can set the values, not reset, force set. So how can I force set? Let's say I want to set the LSB, right? So what we'll do, if I want to set the LSB, so I have this number 1100. So if I want to set the LSB, I will make the LSB 1, all the other rest bits as 0. So it will retain the previous information, just the LSB will be set to 1. So now it will be 1 0 1 1. Okay. So the LSB will be set to 1. That's it. Okay. So yeah, that's basically it. That is what a bitwise OR does. Now what about bitwise XOR? What is the use case for bitwise XOR? Bitwise XOR, the first use case is basically is to selectively complement certain bits. So first use case is selectively complement certain bits. Okay, so how do I selectively complement certain bits? Let's say I have this 0 1 0, or let's say this number only 1 1 0 0. Okay, now I want to selectively complement these two bits. I will make all the other bits to be 0. Okay, and the bits that I want to complement, I will make them 1. Now if I perform bitwise XOR, what is XOR? XOR is odd ones detector, right? So 0 XOR 0 will be 0 only, 0 XOR 1 will be 1, 1 XOR 1 will be 0, 0 XOR 1 will be again 1 only. Okay, so if you observe, like exactly what I have told you, that is that has happened, right? So these two bits has complemented. So these two bits have been complemented simply. This has become 0 1, this was 1 0, this has become 0 1, that's it. So it is used for selectively complementing. Okay, so now what is XNOR used for? XNOR is used for checking whether bits match or not. So that is what XNOR is used for. So XNOR, if you have a XNOR gate, right? So I have this inputs, okay, A, B, and the same number only 1 1 0 0. So if I want to check whether it is equal or not, how will I check whether two bits are equal or not? So what will I do? I will make the rest bits to be 0, but the bits that I want to check the equality, right, I will, like, I can write anything. Now if I take the XOR, this will check whether these two bits are equal or not. Okay, so now what I'm getting, 0 XNOR 0 is simply 1. Okay, 0 XNOR 0 is 1, 1 XNOR 1 is again 1, and 0 XNOR 1 is 0. Okay, so basically you can directly see that as these two bits are equal, that's why I'm getting the output 1. As these two bits are equal, that's why I'm getting the bit as 1. As these two bits are equal, that's why I'm getting bit as 1. As these two bits are not equal, I'm getting 0. So whenever I will get 1, there will be match. So this is used for checking equality of certain bits. Checking equality of certain bits. Okay, that is what XNOR is used for. So I hope you have understood this thing. Yeah, this use case I hope you understood, selecting this and this. So this, it will become 1. If it is equal, it will become 1. Okay. Now what is NOR used for? NOR is used for forcing 0, because there is no way, like we can force 0 here as well, force reset. NOR also we can use force 0, and along with that flip the other bits. Okay, we can force 0 and flip the other bits. What do I mean? So let me show you. So this is my NOR, right? This is my NOR. Okay, so if I have, let's say, the same number 1 1 0 0. Okay, 1 1 0 0. Now if I want to like, let's say I want to force 0 in the middle two bits. So I will make these two bits 1, and I want to flip the other bits. So if I want to flip the other bits, I will make these two 0. So basically 0 is for flip bits and 1 is for forcing 0. Okay, so this will be 1 0 XNOR 0. What will be the, like, if I'm performing XNOR, right? So 0 NOR 0. So first I will perform OR is 0, then it will become 1. Then I will this 0 or 1 is 1 itself. This will be 0. This will be again 0. this will be 0. So what is happening, if you observe, these bits are flipped totally. This 0 became 1, this 1 became 0. Now these two bits were hard resetted to 0 0. Okay, these two bits were hard resetted to 0 0. Okay, so whatever we are doing that is working. Now what about NAND gate? So NAND gate, right, NAND gate is just the opposite. It will flip the bits and also force 1. We can force 1 with NAND gates. So if I have a NAND gate here, AB, okay, if I have a NAND gate, then like this is the initial number again. So let me choose, like if I want to again do the same thing, I want to force 1 in these two bits and flip the other bits. So again you will perform the same thing. You will make 0 the other bits and 1 the bits that you want to perform the force 1. Okay, so what will happen is, sorry, I told you opposite. I told you opposite here, right? You have to do opposite. So basically if you want to flip the other bits, for flipping 1 you have to perform, for forcing 1 you have to write down zeros. Okay, so basically here 0 will force 1 and 1 will flip the bits. Okay, so this 1 and 0 is 0, and if I am performing NAND, this will be 1, this will be again 0. Okay, this 0 and 0 will be simply 1 because I am performing NAND, and this also will be 1. Okay, so if you observe that these two bits are flipped here and these two bits have been forced to 1. Okay, so whatever, like that is the use case of NAND, NOR, or all these things. Whatever we have done, all these operations are synthesizable. Okay, all these operations are synthesizable. So that means, basically this means that I can convert this into hardware, can be converted into hardware. Okay, so that is the thing what I wanted to explain. A few operations, right, will not be synthesizable. I will explain those. Okay, so the symbol, right, I forgot to tell you the symbol as well. Like the symbols I forgot to tell you. So for the AND, the symbol is AND, like this. For okay, this was OR, sorry. For OR, the symbol is like this, just a simple dash. Okay, for AND, the symbol is AND. For for XOR, the symbol is this. This is the symbol for XOR gate. Okay, for XOR, the symbol is this, just doing a not before the XOR. Like I think all the symbols are already here mentioned. Yeah, here. If you can do like this, XOR then not, then you can do not XOR. Both are same only. Both will work. No problem. Nor it will be or then this. Okay, I think it is shown here as well. Okay, it is not shown here, but it should be shown somewhere here. Yeah, if you see, right, both works. Okay, so nor they have not shown anywhere, but nor you can do, right, simply first perform the OR operation, then you do the NOR operation. NAND also is very simple, right, do this. Okay, so these are the two tables for AND OR gate. So I hope you already know this. Just one thing you have to take care, this already I have explained previously as well. If there is don't care or high impedance, then things becomes a bit tricky. That is what you have to understand, except that I have already given you the like truth table of all those things. You can go through this. Okay, I'm not going through it because previously I've already explained this. Okay, so we have this buffer. Okay, so buffer, right, buffer can be modeled but not synthesized in Verilog. Okay, just be careful about this buffer thing. It can be modeled but not synthesized in Verilog. So sometimes your code may not be converted to hardware. Okay, so what I will do is, whatever we have learned, I will give you this question and just tell me what will be the outputs. Okay, these are the simulation that I'm doing. Tell me the outputs. I will not tell you the answer right now. Pause the video in a rough notebook, see the outputs. In the next lecture I will discuss the code, okay, in the computer itself. So I hope you do all this homework. So I will not solve with this. This is the homework for you, assignment questions. Okay, now let's start with this. Let's start with the arithmetic operators. So again, arithmetic operators, you know, plus, minus, multiplication, subtraction, sorry, minus is already done, multiplication, division, and modulus and power. These are the operators. And this you already know. I will not explain modulus. What does modulus do? What does multiplication do? I hope you understand those. Okay. So just few things, few key points I should say, Verilog specific. So plus operator is synthesizable. Is synthesizable. Okay. How we have already modeled adder, so of course you know plus operator is synthesizable in hardware. You already know this, right? Negative is again fully synthesizable. Negative operator is also fully synthesizable. Operator is synthesizable. Okay. So this is using subtractor, and I hope you know we can make a subtractor using a full adder. The hardware you know. Okay, I will not explain that in this lecture. Multiplication is also synthesizable. You can what multiplication is what? Repeated addition, right? Multiplication is repeated addition, so it is synthesizable. Okay, it is a combination of full adders, so this can be made with full adder. How? Basically, if you write c is equals to a plus b, right, a minus b, you can write it like this: c is equals to a plus minus of b. So you convert b to negative and then you perform the addition. That we can do. Okay. Multiplication is simply like synthesizable. How? Y is, let's say, x, like z equals to x into y. So z is x into y. So let's say let's take few numbers, 1 cross 2. Basically what is happening, I'm adding 1 twice. That is what I'm doing, right? I'm adding 1 twice, so it is repeated addition. So we can make this with combination of full adder and half adder. But just keep in mind that whenever we are performing addition, then if I am doing a equals to b plus c, and if these are 4 bits, right, this I have taught in my COA course. Okay, if these two are 4 bits, then the result, right, the highest value of the result will be 5 bits. Okay, for addition. For multiplication, what happens? It becomes like twice of this. If this is 4 bits, the result will be 8 bits. Okay, result will be 8 bits. This information you should know. Okay, about multiplication. Okay, now that is about multiplication. So you need a storage of 8 bits. Now what about division? Division is not fully synthesizable. Okay, division is not fully synthesizable. This is very, very important point to note. Can be asked in interview. Division is not fully synthesizable. So how do we divide? So basically, right, what we do is, if I have y equals to w, if I have some z equals to y by x, how will I divide? It is partially synthesizable. Okay, what do you mean by partially synthesizable? So if I have, if x is a power of 2, that is 2 raised to power n, then I can divide it. How? I will explain. So let's say I have this number 5, I want to divide by 2. What will be the result? Result will be like in if I truncate to integer, result will be 2.22. Okay, because I will truncate to the nearest integer. So how do I perform this in Verilog? So in Verilog we have a thing named as barrel shifter, which we will code later on. Don't worry about it for now. We have a thing named barrel shifter. Okay, so what does this barrel shifter does is, if I have code like this 5, what is this 5? 5 is basically 1 0 0, no, this is 2, this is 4, this one, yeah, this one only, 0 1 2, yeah. So this is 5, right? With barrel shifter, what we do, we right shift each bit. So if it is a 4-bit number, we will right shift everything by 1 if I am dividing by 2. Okay, so if I am dividing this by 2, basically right shift by 1. So what will happen, basically this 1 will be here, this 1 will go away, this will be truncated, this 0 will come here. Okay, and this 0 will come here at the last bit. So 0 1 0 0. So what is this? This is 2. Isn't this what we predicted here? Yes. So that's why, like, we can do the division. If the divisor is a power of 2, then we can just do right shift. If it is n, right, then I have to do n right shift. What is right shift? Don't worry, I will come to that in few like after a few minutes. So just understand that I am right shifting the bits. That is what I am doing. That's it. Okay. So again, modulus operator is also not synthesizable. Okay, modulus operator is not synthesizable at all. So we cannot make hardware. So we will avoid using modulus operator if we know if we have to synthesize the code. Okay, so I hope you know what is basic modulus operator. If I have something like this, 27 modulus 8, so just basically I have to just say the remainder. What is the remainder? Remainder is simply 3 here, so it will be 3. That's it. Okay, very simple. So I have made a question for you, so you can go through the question and try to solve it by yourself. Okay, so let's move on to the next type of operators, that is unary operators. So unary operators are operators that can, okay, like the plus minus can also work as unary operators. Basically, unary operators are those type of operators which only work on one operand. Let me delete this previous page. So unary operators will simply work on one operand. Okay, so just like this, minus 5 plus 5, these are unary operators. These can also work as unary operators. Okay, so minus 5 divide by 2 will evaluate minus 2. Okay, equivalent to 2's complement of 10 and then dividing by 2. So that is what it is doing. So like, just have a quotient on a unary operator. So like the same thing only, nothing changed. So this is very simple. Just I have changed. Okay, I have not even changed this. Okay, so you can solve this. Okay, next, like, there are a few more unary operators, we will discuss about those. Okay, next is logical operators. Logical operators, okay, I may have to discuss about this unary operators somewhere around where is it? Not here, should be, I think they are, okay, not this. Okay, so yeah, we were at logical operators. So what are logical operators? Logical operators, there are three types of logical operator: logical and, logical or, logical not. So and or are binary operators. They operate in two operators. Okay, operator not operator, this is logical not, is a unary operator. It will operate on one of the operand. Okay, one operand. Okay, logical operators follow these conditions. Logical operator always evaluate one value, zero value. Okay, where one is the true or one bit value. Sorry, logical operator always evaluate to a one bit value. So the output of a logical operator will always be one bit value. But this was not the case with bitwise operators, right? So the first difference, I hope you can see clearly. Then what is the output of a logical operator? It can be either 0. 0 means it is false. It can either be 1. 1 means it is true, or it can be x, that is ambiguous. I cannot say whether it will be true or false. Okay, so logical operators can have these outputs: true, false, that is 0 1, 1 0, and cross, ambiguous. That's it. That is the only thing. Okay, so how do I evaluate? So let's read the rules. If an operand is not equal to 0, it is equivalent to logical 1. So anything, right? Let's say 1 0 1, 0 0 1, 0 1 0, anything that is not 0 0 0. If it is not 0 0 0, when we will apply any logical operation, it will be equivalent to 1. That's it. very simple. Okay, it will be equivalent to 1. If it is equals to 0, this will be equivalent to 0 or false condition. This will be equivalent to 1 or true condition. That's the only thing that you have to care about. Okay, if any operand bits is x or z, it is equivalent to x ambiguous condition. But if, let's say, I have this, right, x1 or x0 0, in this case you understand that it is ambiguous, because if this becomes 1, then this will be defined as logical 1. If this is 0, then it will be defined as logical 0. But for this, right, this will also be treated as ambiguous. Okay, although there is a 1 here, still it will be treated as ambiguous. Okay, I don't know whether it will be logical 1 or 0. Logical operators take variables or expressions as operands. Okay, we'll see the examples, they will understand. So this first one is a is 3, b is 0, right? If I perform a and b, this means this is performing logical AND. So while I perform the logical AND, I see a is 3, so it is non-zero, that means a will be treated as 1 or true condition, and b is 0, that means b will be treated as false condition. So it will be equivalent to logical AND logical 0, okay, which is 0 itself. Logical AND logical 0 is 0. Then I perform logical OR, it will be logical 1 or logical 0, which will be 1. This, right, not of a, so not of a will be like this, right, is logical 1, but I am performing not, so it will become logical 0. Okay, it is equivalent to 0. This will be logical, it was logical 0, so it will be logical 1 as I am performing not operation. Okay, now if I have a bit that is x, then I am performing something, right, it will evaluate to x, that's it. Okay, this, right, we can use this as well. A equals to 2 and b equals to 2. If I print, right, it will print true. Okay, because a is 2, in which case if it will print true if a is 2 and b is 3, or else it will print false. It will evaluate to 0 if any of them are not satisfying. So we can use like this as well. So if any of the statements, right, are not satisfying, then it will evaluate to 0. If both the statements are satisfying, then it will evaluate to 1. Now if I want to perform something else, like this is used in relational operators. Let's say I have this a equal to 2 logical or b equals to 3. Okay, so now if any one of the statements is true, then it will evaluate to 1. Okay, so that is the difference between logical AND and OR. For logical AND, all of the statements need to be true, then this will be 1, this will be 1, and then 1 and 1 will be 1. But for logical OR, at least one of the statements need to be 1, then the output will simply be 1, right? If this is true, then it will be 1 or anything, and 1 or anything is 1. Same for b equal to 3. If both are 0, then only the output will be 0. So it depends on your use case, what you want to perform. If you want to satisfy all the conditions, then you will use AND. If you want to satisfy just any one of the conditions, then you will use logical OR. Okay, so I hope you have understood that difference between A and B. So basically, again, this is also like an AND gate only, but this time we are performing logical AND. So if I have A and B, so I will check, this is not bitwise AND. I will check if A is true, if A equal to true, if B equal to true. If both are true, then the output will be true. If even if one of them is false, output will be false. Simple truth table. I hope you know this. Okay. For OR, it is very simple. Even if one of them is true, then output will be true. Okay. If I perform A or B, like if one of A or B is true, output will be true. Here, if both A and B are true, output will be true. Now I hope you understand how the name and OR came, right? Okay, basic thing only. NOT gate is just simple buffer. So nothing much to explain. If it is true, it will become false. If it is false, it will become true. That's it. That is what a NOT gate will do. So basically a NOT gate, if it is true, it will become false. If it is false, it will become true. Okay. So I hope you have understood this thing. So like you can perform this assignment on your own. Okay. Now I will come to equality operators. So equality operators are logical operators that check the equality. Okay. So this checks logical equality, logical inequality, case inequality. So we'll understand each of these operators slowly. Okay. Uh, so when used in expression, it returns logical value 1, that is true, or logical value 0, that is false, if it is true or false. Okay. So these operators compare the two operands bit by bit with 0 filling if operands are of unequal length. Okay. So like what does it mean? So if I have written like this is written, right, a equal b. So if a and b are 4 and 3, right, so it will check each position bit by bit and whether they are equal or not. So if I write here a is 100, right, and b is 110. So first of all the bits are unequal. So what the logical operator will do, logical equality operator, it will first pad a 0, okay, to make the number of bits equal. Now it will check the equality. So I see the first bit is okay, so first bit is okay, so it will give true, but for the second bit it is not equal, right? So hence the overall result will evaluate to 0, that is false. Okay. That's why this, right, a equal b results in logical 0. Now x not equals to y. So x not equals to y results unknown if x or z in a or b. So basically it checks if a is not equals to b. If a is not equals to b, it will result in logical 1. So which is true here, x and y. X and y are not equal because this bit, right, is changed. This third bit has changed. So they are not equal to each other. Hence they will be logical 1. Okay. What about x equal z? Now as z has x, if z has x, then the result will be unknown for logical equality. For this we have case equality. Okay. So what does case equality checks? If a is equals to b including the x and z, so my z is this number and my m is this number. Okay. It will result in logical 1 because all bits match including x and z. So z is matching, x is also matching, everything is matching. So if everything is matching, it will result in logical 1. What about this z equal n? This will result in logical 0 because the last bit is z here, it is x here. So they are not matching, that's why it will result in logical 0. What about m not equal n? It will result in logical 1. So here I have this m, that is 1xxz, and this is xxx, right? So this is the last operator, that is case inequality. So it will check exactly all the bits, and even if one of the bits is not equals to, it will result in logical 1. Okay. So if I would have done here, right, here if I would have done x not equals to z, then also it would have given logical x. Okay. Why? Because it is unknown. Even if one of the bits is unknown, it will just give me x, right? It will not say that okay, this is still like these bits are valid, this is x, so they can be not equals. It will not do that. Even if any one of the operands has a unknown value, unknown bit, it will result in x. Okay, simple for these two operators. For these two operators, we will never get x, right? We will either get 0 or 1, either get 0 and 1. So remember this possible logical values. This is bit important. Okay. So let's see how we will check the equality. Equality is totally synthesizable. Okay, synthesizable. How we can synthesize it? Simply, if I want to check c equals to a equal b, so c will either store 0 or false, right? C will either be true or false. So c will be true if a is equals to b, and c will be false if a is not equals to B. Okay, so how do I check? I will check with a simple XOR gate. Okay, XNOR gate to be precise, with a XNOR gate. So if I perform A XNOR B, it will check, right? If A XNOR B, if I do, basically this is the A XNOR B, right? If I perform, it will either result in 0 or 1. Okay, if it is resulting in 1, that means, if it is resulting in not 0, that means it is logical 1, and that means they are equal. Okay, if it is resulting in 0, that means it is logical 0. Okay, so that is how we will check. So let us do a bit of example. So let us take example 0 1 0. Okay, so now if I do XNOR with this, if I do XNOR with this, let's say this number, right? A is this, B is this, 0 1 0 1. Okay, so if I do XNOR, this will be 0, this will be 0, this will be 0. So all bits are not equal. So let me make few bits to be equal. This will be 1 0 0 0. Okay, so this will be 1, this will be 0, this will be 1, this will be 1. Okay, so few bits are 1 and few bits are 0. So like what we do, right? We check if all bits are 1. If all bits are 1, then the output is given as 1, right? Else it is given as 0. That is the check. Okay, check. If all bits are 1, that means it is equal. So inequality, you will use, how can you synthesize inequality? Inequality, you will simply use the XOR operator. So C is, let's say, Z equals to X not equals to Y. Okay, so this will be XOR. Okay, AB, or I can cite here X Y. Okay, so like let me take an example. So again the same example only, 1 0 1 0. B is 1 0 0 0. So now if I perform XOR, this will be 0, this will be 1, this will be 0, this will be 0. So I know that even if, like, when will this be totally equal? This will be totally equal when all of them are equal, right? So basically, okay, maybe I have done something wrong here, because we can check the equality with XOR gate. Yes, if it is equal, then all bits will be 0. Okay, yeah, you can do XOR gate as well, whatever you want to choose. So here, right, I can see that it is, even if one of the bits is 1, that means it is not equal, right? There is some change. So that means this is true. If I will check, if one of the bits is 1, it is true. If all the bits are 0, that means it is false. If all, you can implement with other hardware as well. I'm just saying you that it is synthesizable. We can implement it with hardware. Okay, if all bits are 0, true if all bits are true if, like, if any one of the bits, any one of the bits is non-zero. Okay, so that is the thing that I wanted to explain. So this case equality and inequality, right, is not synthesizable. Okay, so case equality and case inequality both are not synthesizable. So just be careful regarding these things. Okay, both are not synthesizable, so they cannot be converted into hardware. Okay, they cannot be converted into hardware. Okay, so I'm giving you a homework, try it out by yourself. So like just write on a rough notebook what will be the solutions and answer. Now let's come to the next type of operators, that is relational operators. So just hold on, I will check one thing. So relational operators are what kind of operators? Relational operators are greater than, less than, greater than equals to, or less than equals to. Basically they relate, right? If some number is greater than, then it will evaluate to true, else it will evaluate to false. Let me give you example. I have 4 and 3, right? So if I perform a less than equals to, so is a less than equals to b? No, it is false, so it will evaluate to logical 0. A greater than b, is a greater than b? It is true, so it will evaluate to logical 1. X greater than equals to x, y greater than equals to x, is y greater than equals to x? Again I have to check bit by bit, right? So this bit is greater than here 1, then this bit is here more, this bit is here more, this bit is here. So like ultimately it will evaluate to 1 because you are checking with the decimal number, but there is a boolean expression for this which we will check, which we will do. How we check if a number is greater than or not, I will show you. Okay, and this one is if x, y is less than z, it will evaluate to x, because even if one of the bits is x, then the whole result will be taking x. If there are any unknown or z bits, the expression takes a value of x. That's it. Okay, so now let's understand how can I code greater than and less than to understand that whether these are synthesizable or not. So how do I code greater than operator? Okay, greater than operator. So if I have two 1-bit numbers a, b, so what I observe is if a is 1 and b is 0, then my greater than expression, right, should evaluate 1 because a is greater than b. So I am checking a, my c is equals to a greater than b. Okay, so this will evaluate true. If a is 0 and b is 1, then this should evaluate 0, correct? So how do I code it basically? So basically what we are doing, C expression, if I want to write a boolean expression, it will be a b bar. That is what we are doing. So if I now perform, if a is 1, like you can do, like you can develop equation boolean expression with using the truth table, k map, all those things you can do. Okay, so if a is 1 and b is 0, then c evaluates to 1. If b a is 0, then c should evaluate to 0. That's it. It doesn't care about b. Okay, so that is what we are doing here. So that is for a small equality. Okay, so what we have to check for, this is for a single bit. Now what about for multiple bits? Multiple bits. Okay, how do I solve for multiple bits? So for multiple bits, basically C will be equals to, let's say I have a 3-bit number. Okay, not 3, sorry, 4-bit number. Okay, so my number is a of 3, a of 2, a of 1 and a of 0. So it is a 4-bit number. This will be b of 3, b of 2, b of 1 and b of 0. Okay, so how do I check? So first what we will do is I will check if the highest bit is more. If the MSB of A, let's say if the MSB is 1 and the MSB of B is 0, that means like problem solved, right? I don't have to check all the other bits. Automatically I know my A will be higher because MSB is 1, so it is the highest weightage. So if it is 1, so of course automatically everything is done. So first I will check the first MSB bit, most significant bit. If I check the most significant bit, if it is true, then of course I don't need to evaluate the other things. So how do I check this with this, right? So basically it will be a of 3 dot, or and you can say, dot means and in boolean expression, b of 3, not b of 3. Okay, so if this is true, then I don't need to evaluate anything else. But if this is not true, right, then I need to evaluate the next MSB. So again I have to perform or now that means these are equal. So I have to check if these are equal or not. If these are equal, then only I will proceed to the next one. else I will not proceed to the next one. So if these two are equal, how do we check equality? Equality, how do you check? You check equality with x naught. Okay, you check equality with x naught. So this will be a, they have to be equal. So it will be a2 x naught of b2. Okay, this, if this is true, that means the MSB is equal. If MSB is equal, then only I will move. Okay, else if the MSB is not equal, that means what other case is left? So one case is taken care of if my A is greater than B. Okay, that is taken care of. If this is, if my A is 1 and B is 0, that means this expression will yield what? This expression will yield 1. If this yields 1, then I don't need to check anything else, right? I am done. I am done. Okay, but let's say they are equal. If they are equal, then I have to check whether they are equal, then I will check something else. But let's say they are not equal. If B is 1, that, do I need to check the other bits? No, right? If the MSB of B is 1, that means by just observing, I can say that no, they will not be, like A will not be greater than B, B will be greater than A. Okay, so I don't need to check. So just keep a mind of this thing. Okay, so I will explain this in a bit. For now, let's do the equality. So if they are equal, that means I have to check the next MSB. Check the next MSB. So MSB equal. Then I will check the next MSB. Next MSB will be this. Okay, this one. How do we check the next MSB? Just like this. But here bit position 2 will be there. Okay, so it will be A of 2 dot B bar of 2. Okay, same thing again I will apply. This checks whether A of 2 is higher than B of 2. If they are equal, then again I have to check the next bit. So same thing I have to follow here again, that if these two are equal, so I have to take the case again. If A of 1, not A of 1, sorry, I made a huge mistake. This should be A of 3 and B of 3. Okay, I was checking the MSB. Okay, now I will check if A of 2 is equals to B of 2. Okay, if these two are equal, then I will move again the same condition. Then I will check this bit. Okay, so I am moving slowly. 1 and B bar 1, and same for the last case. I will check the next bit. If they are equal, then I will check the last bit. A of 0 and B of 0. Okay, so that is what I will get. So just be careful about this thing. So I will explain now. I will explain. So what we do is, first we check these two bits. If these two bits, like if A is higher than B, so basically if this is 1 and this is 0, then I don't need to check anything else. Then automatically this evaluates 1. Then automatically I don't need to check this. I get C as 1. Next, what I need to check is if both are 0. If both are 0, then only I will go into the next condition. If both are not 0, right, then this will evaluate what? This will evaluate 0. So I have checked for the case of 1 0. I have checked for the case of 0 0, which this evaluates 0. This evaluates 0. Okay, for the case 0 0. Okay. If this evaluates 0 0, and what does this evaluate? This will also evaluate what? This will also evaluate, like if let's say if B is 1 and A is 0, this will evaluate 0. Okay, this evaluates 0, this evaluates 0. So ultimately C will be 0. Then A is not greater than B. That is what we will get to. That is what I will get to if you evaluate this slowly. Okay, if you evaluate this slowly, you will see that you are getting 0. You are getting 0. Okay, so you can take a small example, then see. Now I will check if these two are equal. If these two are equal, that means I will check the next bit. So why is this important? Let me take an example. Okay, so I have this 1 1 0 0 and 0 1 0 0. Okay, so first I took this example. I see the MSB is higher than this MSB, right? That means this number will be higher. So now if I make this equal, that means these two numbers are equal, then I will check the next highest weightage number. Next highest weightage number is this one. Again these two are equal. If these two are equal, again I will check the next highest weightage number. Let's say here if this is 0 and this is 1, okay, that means what? Again the number B became higher than A, so it should evaluate 0. Let's check in the code if it evaluates 0 or not. So of course this is equal, so this will evaluate 0 because A is 0. This will evaluate what? This will evaluate, they are equal, so this will evaluate 1. This will evaluate what? This will evaluate this one, right? So it evaluates again 0 because this is 0, okay. Again my A bits are all 0, right? It will always evaluate 0, so ultimately I will get 0. So you can evaluate for any number. Let's say now if I change this, okay, if I change this to 1, this to 0, then what will happen? Let me do this. Then what will happen is these are equal, so I will move it here. Then I will check the MSBs, they are equal. Then I will check this A2 and B. So A2 is 1 and B2 bar is again 1. So I evaluate 1. This is 1, this is 1. So ultimately I don't need to evaluate all this. My final expression will be 1 automatically. So I hope you understood this point. Now we will code the less than operator, okay. Similar thing for less than operator, just a bit opposite, So again first let me write here less than operator. So now I will do this a bit fast. Less than operator. So less than operator, what do we see? AB, okay, 0 1. So this will evaluate true only if B is 1 and A is 0, right? Then only it will evaluate true, that A has to be less than B. So basically this is my final expression, A less than B. So what like in Boolean logical expression, what it will be? It will be A bar B, A bar B, okay. This will be your final expression. So now again the same thing, same way I will code. So what I will code is, I will write my C. First I will check the MSB. Again I have 4 bits. I will check the MSB. If the highest bit is lower than the, like let's say this number, right, 0 1 0 0 and this 1 0 0. If the MSB of A is lower than MSB of B, that means automatically my E will be lower than the B automatically, right? That will be always valid. So automatically I don't have to check anything else. So that's why I will do this as E3 B3, okay. It will check whether the first bit is MSB is lower than the lower than the MSB of the other number. So I check, if I do A bar, this will be 1 and this will be 1. It evaluates 1, so I don't need to evaluate anything else after this. But if they are equal, then I need to again move on to the next bit. Similar pattern as we have solved in the previous greater than equal to operator. So now I will just write the expression, okay. This will be A, first I have to check equality, A equality B, okay, X nor B, then multiply it with A2 bar B2, okay. So like this will just get repeated until 0, okay. This I already have explained. Now what about the greater than or equals to operator? If I have greater than or equals to, what about this? Okay, so for greater than equals to, just additional one thing will be there. So basically, right, what I am doing currently is like I am just making a Boolean expression. So if A is 0 0, if A is, like we can make a Boolean expression, right? A is 0 0, A is 0 1 1 0 1 1. So what will be my output? If A is 0 0, output will be 0, else it will be, this will be 1, this will be 0, this will be 0. And here also we have done the same. Like this is how you will derive the logical expression. I did not mention at first. I should have mentioned this that point of time. See, so this will be A 0 0, C will be, in this case both are equal, so it will not be greater than if it is 0 1, correct. If it is 0 1, then again it will be false. If it is 1 0, it will be true, else again it will be false, okay. In this case, right, in this case again you can derive the K map or write the Boolean expression from this directly, okay. So here again the same thing only. I have A B C. A is 0 0, 0. If they are equal, yeah, if they are equal, it will be 1. If they are not equal, if B is greater than C, I will get 0. If A is greater than C, again I will get 1, and if both are equal, again I will get 1. Okay, so what is this? Like, you can again derive the Boolean expression for this. It will simply come out to be C, not C, sorry, A or B bar. That is what your expression will be. So what you can do is, like, you can write it like this, or what you can do is, if we have multiple bits, you have already solved for the greater than operator. Okay, greater than operator, you do a OR for checking the equality. Just do A XNOR B. If this evaluates true, then I will get 1. If greater than evaluates true, then I will get 1. Either they are greater than or they are equal to. If any one of them is true, I will evaluate to 1. So this is already solved. Just I have to check the equality. That's it. For less than as well, same thing. For less than as well, same thing. So the truth table for less than A, B, C, this is 0, 0, 0. Again they are equal, so this will be 0, 0, 1. This will be 0, 1. So again this will be true. This will be 1, 0. This will be false. This will be 1, 1. This will be true. Okay. So for this, you can derive the expression. Okay. It will come out to be simply C is equals to A bar B. Just the opposite. A bar B. Okay. So if you have multiple bits, again you can do the same thing. Your C, like here, this should be your this should be a C. Okay, so your C is basically what? Your C will be, first I will check the less than condition, less than operator, then what I will do, or with the equality. If they are equal, then this will evaluate true. So again it will be A X not B. Okay, they will evaluate true. That's it. That's the logical expression. So for this you have the homeworks. You can solve the homeworks. Okay, so now we will discuss about reduction operators. So what are reduction operators? Reduction operator perform bit by bit operations but with a single operand. So they are also a type of unary operators. Okay, so that's why they are also a type of unary operators, because unary operators have single operands. Okay, so reduction operators perform bit by bit operations. So we will see this. First I have AND. So if you see, this is same as bitwise AND. Okay, it is same as bitwise AND, but as I am performing operation on a single operand, then it will be what? It will, Verilog will understand, the compiler will understand that it is a reduction operation. Okay, so if I do AND here, and if let's say X is 1, 0, 0, 1, 0, so what this AND X means, perform AND with all the bits of X. So 1 and 0, 1 and 0. Okay, so obviously you know this will be 0. So that's why this evaluates to 0 as written over here as well. Not X. Oh no, sorry, not this is not X. This is OR X. Okay, OR X basically means that perform the OR operation. So it will be 1 or 0 or 1 or 0. Okay, this will be again evaluate to 1. Okay, as it is written over here. Then XOR X. So it will, like, same thing only, it will perform XOR with all of the bits 0, XOR 1, XOR 0. So this will be 1 XOR 0 is 1, then 1 XOR 1 is 0, 0 XOR 0 is 0. So ultimately output will be 0, as you can see from here. Like you can do, and many other things are there. XNOR also you can do, other things also you can do. Okay, this is used for sometimes checking even odd parity. Okay, this is used for sometimes checking even or parity. Okay, so very simple. Like, is it synthesizable? Yes, of course it is synthesizable, right? Simply, how can I synthesize it? If I, let's say, I want to do AND operation, right? Reduction AND operation. So I have this value X. So I will feed this 4-bit X value here. Okay, 4-bit X value I will feed it here to a AND gate, 4 input AND gate, and the output I'll store. Okay, and that will be the value. Simple, right? Just bit by bit I will send to an AND gate and will store. Same for OR gate, same for XOR gate, same for NAND gate. Okay, you have, how can you build an AND gate? You have a AND gate, then you put a NOT gate, you get a NAND gate. Okay, so sometimes they are very useful for logic design. They are very useful for logic design, like for checking even parity or odd parity. Okay, they are very useful. So again, another question on reduction operator. Just I have this test bench. Try to solve what will be the output. What will be the output? Try to solve after doing all this. Okay. Now let's discuss about shift operators. So shift operators basically move to the bits to the right or the left depending on the number that is given to them. So there are 4 types of shift operators: right shift, left shift, arithmetic right shift, arithmetic left shift. Regular shift operators shift a vector operand to the right or the left by specified number of bits. Okay, so if I write here x, this is the right shift 1, that means shift all the bits by 1. Okay, by position 1. So this will simply become like this bit, this right last bit will go to the dustbin because I'm shifting it to the right. I don't have anything to the right, it will go to the dustbin. This second LSB will go here, this will come here, this will come here. Now this position is empty because this bit has gone to the right hand side. So for a regular right shift, we replace the empty position with 0. Okay, so ultimately it will be 0 1 1 0. Okay, so that is what is written over here. Okay, what about this one? Left shift, same thing only, but I will move everything to the left hand side now. Okay, so this will be basically basically this, what will happen is, if I have a number 1 1 0 0, I'll move this to the left, this to the left, this, just hold on, this to the left, but to the left of this MSB, right, I don't have anything, so this will go to the dustbin. Okay, so this is vacant. If this is vacant, again I will fill it with 0. So that is what I am getting, right? Every what I am getting is, it will be 1 0 0 0, which is exactly written over here. What about, like, if I left shift 2? If I left shift 2, this 0 will come here, this 0 will come here, this 1 will go to the dustbin, this 1 will go to the dustbin, everything will be 0, which is shown here. Now there is another thing known as arithmetic left shift and right shift. So just remember this thing: arithmetic left shift and right shift is used for signed data type integers. If I write a very important statement, if number is positive, then it will work like regular shift. Okay, it will work like regular shift. If the number is not positive, then it will not work. Okay, then obviously it will not, it will work obviously, but it will work differently. Okay, so we have to think about that, we'll discuss about that. Okay, if the number is positive, then don't have to worry about anything, just apply simple whatever we have learned here, apply the same concept. One more thing I forgot to tell you is that if I apply right shift, right shift, there is a shortcut to right shift. What is the shortcut to right shift? The shortcut to the right shift is, if let's say x right shift 1 is written, then it will be x divided by 2, the integer, obviously the integer value of x divided by 2. If it is x right shift 2, that means it is equals to x divided by 2 square. If it is 3, it will be x divided by 3, 2 raised to power 3. Okay, it will go on like that. I hope you have understood, like, this is the shortcut. Left shift also there is a shortcut, but not for this case. Also, how to implement this is synthesizable. Arithmetic right shift and arithmetic left shift is not always synthesizable, but regular right shift and left shift is synthesizable, and that we will discuss later on. That is known as barrel shifter, that we will discuss later on. Okay, now let's discuss about arithmetic shift. Okay, So if I am performing like logical right shift and left shift, I hope you understand. What about arithmetic? So for positive numbers, there is nothing wrong. It will be same. Okay, it will work as it is. So let's say if I am performing this, right, positive 10. So positive 10 in binary is 1 1 0 1 0. So if I am performing right shift by 3, so this one will come here, this 0 will go to the dustbin, this one will also go to the dustbin, this 0 also will go to the dustbin, rest of everything will be filled with 0. So this will be 0 0 0 1. So ultimately the result will be 1. Okay. Now what about a negative number? For a negative number, what we do, it retains the sign bit for signed integer. Okay, for negative number it will retain the MSB. So let's say this integer is b minus 20. b minus 20 means that what is happening is that my sign bit will be retained. So how is minus 20 represented in your Verilog? In 2's complement format. So let me write the 2's complement format. So what is 20? 20 is this one, right? 20 will be so 0 2 4 then 8 then 16. So this is my 20. Okay, this is my 20, and of course I will have a sign bit here somewhere here. So like this is a 32-bit number, so there will be zeros in between, and ultimately this will be my minus 20. Okay, and this will be the MSB, that is the 31st bit, 31st position. Okay, how do I store it? So we take the 2's complement of this, right? We take the 2's complement. So 2's complement, this will be 1 1 goes on until here 1, then this becomes 0, this becomes 1, this becomes 0, this becomes 1 1, then I will add 1 with this. So ultimately it will become, this will be 1 1, it will be 1 till here, this will be 0, this will be again 1 is there, 1 1 0 1 is there, this will be 0, this will be 1, this will be 1, this will be 0. Okay, so ultimately you will get this, ultimately you will get this. Okay, what it will do, it will retain this bit, this bit will be still here. Okay, arithmetic right shift, now I have to do arithmetic right shift by 3. So I will do the right shift by 3 now. Okay, I will do the right shift by 3 now. So what will happen is that this one will come here, this one will come, this one will come here. Okay, right? No, I am doing arithmetic right shift by 3, so this is 3. So okay, after 3 bits, right, this first bit, second bit, third bit, so this one will come here, this will be first bit, second bit, third bit, this will be first bit, second bit, third bit, this one will come here. Okay, so basically what will I get? This will be 1. Okay, then it will be 0, then it will be 1, and after that, right, everything is 1, so everything will be 1. Okay, everything will be 1 after this. So now how do I come back to my original number? To come back to my original number, again you have to take the 2's complement. So 2's complement will be complement of this number, that is 0 0 1 0, and rest are all ones, right? So this also will become all zeros. Okay, and obviously on the MSB I have 1, this will not change, this will be 31. Okay, so this will be what? This will be, then I have to add 1, so this will be 1 1, and MSB is still 1. Okay, and rest all these are 0, rest all these are 0. Okay, so what is this? This is simply 3, and MSB is 1, that means it is negative 3. So I get the answer as negative 3. Okay, so I do understand it is a bit hectic, but is there a shortcut to this? Is there a shortcut to this? So what if I would have done right shift 2? Let's check for that. If I would have performed x right shift 2. Okay, so if I would have performed x right shift 2, then what would have happened? Then this bit would have reached here, this would have reached here, this would have reached here. So basically this 1011 would have been here, 1011, correct? So I will have 1011, and rest all will be all ones, because all these will be right shifted by ones, but I will have few zeros here, right? I will have few zeros here. Okay, don't forget these zeros. Okay, now remember, it retains the sign bit for the signed integer. So whatever was the sign bit, right, it will fill the remaining bits also with sign bits. This, right, remember, if I had few ones here, as I move right shifted, so all this will be also filled with the sign bits. Okay, all of this will be filled with 1. Okay, don't get confused, all of this will be filled with 1s. So this ones will be filled. So I will write here the vacant positions. For positive number you don't have to take care, just for negative number you have to do all this circus. Vacant numbers will be filled with 1. Okay, here also everything else will be 1 only, rest of them will be 1. Again, if I take the 2's complement now, this will be 0 0 1 0 0 0 and everything is 0. Okay, so now again I have to add 1. So if I add 1, this will become 1 0 1, which is equals to what? This is equals to 5. Okay, and of course I have a sign bit at the front, that is -5. So basically, right, what we are doing, if you observe, this is -20 divided by 2 raised to power 2, that is minus of 4. Sorry, not minus of 4, sorry, minus of 5. Okay, you observe we are doing this. Here what we are doing, here we are doing minus of 20 divided by 2 raised to power 3, that is minus 20 divided by 8. So this is equals to what? This is equals to this, if I write 20 divided by 8 is equals to minus 2.5. So it chooses the, like if it is at minus 2.5, right, it will choose -3. That is what you have to do. Okay, so you can do this. This is the shortcut. In the next lecture I will also like exactly tell you the formula, because we will run the code and we will see the output. Don't worry about this. Okay, so arithmetic shift is just a bit tricky, and I don't think this will be asked because this is not always synthesizable. Okay, not always synthesizable. All compilers will not be able to synthesize this, not always synthesizable. So you should know what is synthesizable and which is not synthesizable. You have to refer to the synthesis document of that particular compiler. So refer to the synthesis document. Okay, that is what you need to do. So yeah, that's it basically. You can pause the video, try it out by yourself. This is the homework for you guys. Now we will do few more operators are left, like concatenation operator and replication operator. So what is concatenation operator? Concatenation operator appends multiple operands to create large vector. Like this already I have explained previously as well. So this Y is combination of B and C. So what is B? B is a 2-bit number, C is a 2-bit number. So if I concatenate the two, basically what will happen, the result will be 0 0, the first MSB, and this will be 1 0. So this will be at the position leftmost, this will be at the rightmost position. Basically I am concatenating the two, that's it, simply concatenating the two. But just remember here, order matters. Okay, order matters, order will matter here, just be careful regarding that. Okay, next is A, B, C, D, and like you can write numbers here as well, that is also totally valid. So this will again concatenate. So A will come first, that is 1, then this B will come, that is 0 0, then C will come, that is 1 0, then D will come, that is 1 1 0, then I have this 0 0 1. So I hope you understand this. We can use slices of vectors as well, single bit as well, or we can use a range of bits as well. Everything is valid, everything is valid. Okay, next is replication operator. Replication operator simply replicates. Okay, creates repetitive copies. Just like if I write 4 bracket curly bracket A, that means it will replicate A 4 times. The result will be simply A is 1, so it will be 4 ones. Okay, I hope you understood the same thing. It is similar to that only. Last one is the conditional operator. So conditional operator we have already used previously, and this is totally synthesizable. How will you synthesize? With mux, with mux basically. So this is totally synthesizable. So like it is especially used in multiplexer, returning one of the two values based on the condition. So let's say this control question mark in 1 in 0 is there. If control is logic true, then in 1 will be stored in result. If control is logic 0, then in 0 will be stored. I hope you now know what is logic 0 and logic 1. This is exactly like a 2:1 mux. Exactly, ditto like a 2:1 mux. So same thing I am doing here only. So but we can nest the conditional operators as well. So the first one is, first it will check if a is equal to 2. Sorry, if a is equals to 3. If a is equals to 3, then I will perform this operation. If it is not true, then I will perform this operation. Let's say it is true, a is equals to 3 is true, then I will go into this, then again I will check, perform this operation. Now when I come to this operation, then I check, I have another conditional operator. So I will check whether control is true. If control is true, then I will return x. If control is false, then I will return y. Let's say control is true, that means it is logical true. I hope you know what is logical true. In this lecture itself I have explained. So logical true, that means x will be returned here. So x is returned here. Finally this will return x to the output. Okay, so we can nest our ternary our conditional operators as well. So last one is, if multiple operators are used together, then there has to be certain rule of precedence. What does precedence means? Who will get the highest priority? Operators in Verilog follow a specific follow of precedence from highest unary operators to lowest conditional operators. So conditional operators has lowest precedence. So if multiple operators, like this equality operator is used, so first equality will be checked, then this conditional operator will be executed, because equality operator has higher precedence than conditional operator. Okay, so I hope you understood this, like in what sequence the compiler will compile the code, that is the precedence meanings. But what we suggest is you use parenthesis for better preference, because once I use brackets, right, what does brackets means? First perform this, then you do anything else. So in our code we will use brackets to avoid any ambiguity, because if I leave anything to the compiler, some error or something I might get. So I don't want that. Okay, so whenever I want to perform an operation first, I will use brackets. That's why here I have a brackets. Brackets mean this will be performed first. Okay, whatever happens, this will be executed first. Okay, I hope you have understood this. Now I wanted to, like, I've already given you code homeworks, so I want to give you a few question homeworks as well. Just pause the video and try to do on your own rough notebook or somewhere else, and in the next video I will solve all these questions. And obviously I have given you the codes as well. We will see the codes of these whatever we have learned operators as well. Okay, so just take a pause and try to solve all this. So that's it. If you did enjoy this video, don't forget to hit the like button and make sure to comment on the video, so that students can understand how, like, what is the level of content that you are receiving. And make sure to comment on the first video as well, because students start watching from the first video, and if they see a good response on the first video, then they will continue. Okay, so like, I hope this much you can do for me. I am doing this much for you guys. So thank you for watching, and I hope to see you in the next lecture. Until then, happy learning.